Chapter 10. Gravitation.
Gravitation. We know that a force is required to move or stop any moving object. Consider some examples of motions. Throw a ball in upward direction. Observe what happens. The ball reaches a certain height and then falls downwards. During rainy season, the raindrops fall straight on the surface of the earth. Fruits fall to the ground when they get detached from the plant. Which force is responsible for bringing the ball, raindrops, and fruits down to the earth? Objects or things fall down to the earth because the earth pulls them. The force applied by the earth to bring the objects down is called gravitational force. A force is exerted by the earth on an object due to which it is attracted towards the earth. This was discovered by Sir Isaac Newton. There is a small anecdote related to this. Newton was sitting under a tree when an apple fell on him. The fall of the apple made Newton to think. He pondered on the force responsible for its fall towards the earth's surface. He thought that if apple is attracted towards the earth, then why it cannot get attracted towards the moon? Is the force same in both the cases? Newton observed that all bodies are attracted by the earth towards its center by some force, which he named as gravitational force. Newton generalized this idea and stated that gravity is not a property of the earth alone. In fact, every particle in the universe attracts every other object. He studied motion of the moon around the earth. The moon rotates around the earth in a circular orbit. The moon falls towards the earth under the action of gravitational force, but due to its horizontal velocity, it moves in circular orbit. Let us try to understand the motion of the moon by an activity. Take a piece of thread. Tie a small stone at one end. Hold the other end of the thread and whirl it around. Release the thread. What do you observe? The stone moves in a circular path with a certain speed and changes direction at every point. At every moment, it has a velocity along the tangent. The change in direction involves change in velocity and hence the acceleration. Thus the stone is accelerated towards the center. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center along the string. This force is called the centripetal, means center-seeking force. When we release the thread, the stone flies off because there will not be any centripetal force acting on it. The motion of the moon around the earth is due to the centripetal force. The centripetal force is provided by the force of attraction of the earth. If there was no such force, the moon would pursue a uniform straight line motion. It is seen that a falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Why? The apple does attract the earth with equal force. But according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. The mass of an apple is negligibly small compared to that of the earth, hence the acceleration of the apple is very large compared that produced in earth. So we do not see the earth moving towards the apple. In the same way, earth does not move towards the moon. In our solar system, all the planets go around the sun. Therefore, there exists a force between the sun and the planets. This force of attraction between objects is called the gravitational force. Newton's law of gravitation is also known as universal law of gravitation. Universal law of gravitation. According to Newton, every object in the universe attracts every other object with a force, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Let m1 and m2 be the masses of two bodies lying at a distance r apart, and F be the force of attraction. Then, according to Newton's law of gravitation, F is directly proportional to m1 into m2 and F is inversely proportional to r square. Combining both equations, we get F is directly proportional to m1 into m2 upon r square, or F is equal to g into m1 m2 upon r square, where g is constant of proportionality and is known as universal constant of gravitation. If we put m1 is equal to m2 is equal to 1 and r is equal to 1, then F is equal to g multiplied by 1 multiplied by 1 divided by 1 square. F is equal to g, or g is equal to F. Therefore, universal constant of gravitation is the force of attraction between two unit masses placed at unit distance apart from each other. The value of g does not depend upon the nature and size of the bodies. It also does not depend on the nature of the medium between the two bodies, hence it is called the universal constant of gravitation. From the equation F is equal to g into m1 m2 upon r square, we get g is equal to f r square upon m1 m2. Now let us see SI unit of g. Substituting the units of force, distance and the mass in the equation, we get SI unit of g is equal to Newton meter square per kilogram square, or Newton meter square kilogram raised to minus 2. Value of g. The value of g can be determined experimentally. It is found to be g is equal to 6.673 into 10 raised to minus 11 Newton meter square kilogram raised to minus 2. In SI unit, or g is equal to 6.67 into 10 raised to minus 8 centimeter square gram raised to minus 2. in CGS system?
We can see that the gravitational force between two bodies is inversely proportional to the square of the distance between them. Which means, if the distance between the two bodies is doubled, the gravitational force becomes 1/4. On the other hand, if the distance between the two bodies is halved, then the gravitational force becomes 4 times.
We know that there exists a force of attraction between any two objects. Do you experience the force of attraction between you and your friend when both of you are sitting close by? No, since the force of attraction is very small and negligible to move towards each other. Let us find the force of attraction due to gravity between two objects of masses 40 kg and 50 kg respectively. Let the distance between them be 0.5 meter. The value of F is given by the formula. F is equal to G into m1 m2 upon r square. Substituting, r is equal to 0.5 meter, m1 is equal to 40 kg, m2 is equal to 50 kg, and the value of G is equal to 6.67 into 10 raised by minus 11 into nm square upon kg square. F is equal to 6.67 into 10 raised to minus 11 into 40 into 50 divided by 0.5 into 0.5 is equal to 6.67 into 40 into 50 into 10 raised to minus 11 upon 5 into 5 into 10 raised to minus 2. Simplifying, F is equal to 536 into 10 raised to minus 9 Newton is equal to 5.36 into 10 raised to minus 7 Newton. This force is negligibly small to move the bodies towards each other. Now let us find the force between the two bodies, out of which one is large in size. Now let us find the force between a man of 60 kg and the earth. Mass of earth is equal to 6 into 10 raised to 24 kilogram. F is equal to G into m1 m2 upon r square. Here m1 is equal to 60 kg. m2 is equal to 6 into 10 raised to 24 kg, and radius of the earth is equal to r is equal to 6.4 into 10 raised to 6 meter. Substituting the values in the equation, F is equal to 6.67 into 10 raised to minus 11 into 60 into 6 into 10 raised to 24 upon in 6.4 into 10 raised 6 whole square. Simplifying, we get F is equal to 586 Newton. This is an appreciable force which is easily felt by man. Thus, if any one body between two bodies is large in size, the gravitational force will be quite large. This force is called the force of gravity. The Earth exerts a force of gravity equal to 586 Newton on a man of 60 kgs standing on the surface of the Earth. Now, let us solve few examples based on what we have learned so far. Solved examples. A stone of mass 2 kilograms is falling from a certain height. Find the force of attraction between the earth and the stone. Also, find its acceleration. Solution. First, let us write the given quantities. Mass of the earth, m, is equal to 6 into 10 raised to 24 kilogram. Mass of stone, m, is equal to 2 kilogram. Distance between stone and center of earth is equal to the radius of the earth. Radius of the earth, r, is equal to 6.4 into 10 raised to 6 meter. Constant of gravitation, g, is equal to 6.67 into 10 raised to minus 11 in SI units. We know F is equal to G into capital M small m upon R square. Substituting the given values, F is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 into 2 upon 6.4 into 10 raised to 6 whole square. Simplifying, F is equal to 19.6 Newton. Therefore, the force of attraction between the earth and the stone is 19.6 Newton. Now, the acceleration produced in the stone is given by acceleration g is equal to F upon m. Therefore, g is equal to 19.6 upon 2 is equal to 9.8 meter per second square. Therefore, acceleration is equal to 9.8 meter per second square. 2. If the force of gravitation between the earth and a body of mass m is 9 into 10 raised to 7 Newton, then find the mass of the body. Mass of the earth is equal to 6 into 10 raised to 24 kilogram and the radius of the earth is equal to 6.4 into 10 raised to 6 meter. First, let us write the given data. Given force F is equal to 9 into 10 raised to 7 Newton. Radius of the earth, r, is equal to 6.4 into 10 raised to 6 meter. Mass of the earth, m, is equal to 6 into 10 raised to 24 kilogram. Universal gravitational constant, g, is equal to 6.67 into 10 raised to minus 11 Newton meter square per kg square. Formula to be used is F is equal to G into capital M small m upon R square. Substituting the given values, 9 into 10 raised to 7 is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 into m upon 6.4 into 10 raised to 6 on the whole square. M is equal to 9 into 10 raised to 7 into 6.4 into 10 raised to 6 on the whole square upon 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24. Simplifying, we get m is equal to 9.2 into 10 raised to 6 kilogram. Hence, the mass of the body is m is equal to 9.2 into 10 raised to 6 kilogram. Importance of the universal law of gravitation. The universal law of gravitation successfully explains the force that binds us to the earth, the motion of the moon around the earth, the motion of the planets around the sun, and the tides of the sea due to the moon and the sun. It is the force responsible for motion of galaxies. We know that there exists a force of attraction between any two objects. We are exerted by attractive forces by all objects surrounding us. We do not experience it because of its small magnitude due to the small masses of the involved objects.
In the 16th century, the great German astronomer Johannes Kepler proposed 3 laws governing the planetary motion. The laws describing planetary motion are also valid for describing the motion of satellites, like the moon around the earth. The 3 laws of planetary motion are: Kepler's first law states that planets move around the sun in elliptical orbits, with the sun at one of the foci of the eclipse. Kepler's first law shows that the orbit of planets around the sun is not a perfect circle, but is an ellipse or oval-shaped. We know that an ellipse has 2 foci. The sun is situated at one of the foci of the ellipse. Kepler's second law states that every planet revolves around the sun in such a way that the line joining the sun to the planet sweeps over equal areas in equal intervals of time. We know that a planet moves around the sun in an elliptical orbit, with the sun at one of the foci of the ellipse. Since the line joining the planet and the sun sweeps over equal areas in equal intervals of time, it means that a planet moves faster when it is near the sun and moves more slowly when it is further away. This implies that the speed of planets orbiting around the sun is not constant. The speed of planets revolving around the sun will be constant only if the orbit is a true circle rather than an ellipse. Kepler's third law states that the cube of the mean distance of a planet from the sun is directly proportional to the square of its orbital period. We can express this mathematically as r cube is directly proportional to t square, where r is the mean distance of the planet from the sun, while t is the time taken by the planet to move around the sun, that is, the time period of the planet, or r cube is equal to constant multiplied by t square, or r cube upon t square is equal to constant. Fall. Let us consider an example to understand the meaning of free fall.
Throw a ball in upward direction. What do you observe? We observe that the ball slows down as it ascends. It reaches to a certain height and falls down. When a body falls towards the earth under the influence of the earth's gravity alone, its motion is called free fall. If an object is released from some height above the surface of the earth, it falls freely on the earth's surface. As the object is under the action of the earth's gravitational force, its velocity goes on increasing. Increase in velocity means acceleration of the object. This means a falling object moves with acceleration. This acceleration is due to the gravitational force. Therefore, this acceleration is called acceleration due to gravity and is denoted by g. Let us define acceleration due to gravity. The uniform acceleration produced in a freely falling body due to the gravitational force of the earth is called the acceleration due to gravity. Now let us derive the formula for g. Let an object of mass m release from a distance r from the center of the earth. Let the mass of the earth be m. According to Newton's law of gravitation, F is equal to g into capital M small m upon r square. According to Newton's law of motion, the acceleration generated in the object is given by acceleration is equal to force upon mass. G is equal to F upon m. Substituting for F in the above equation, we get G is equal to capital G capital M small m upon small m r square. Cancelling the common factor m, we get G is equal to capital G capital M upon capital R square. From the above relation, we can understand that acceleration depends on the mass of the earth, m, and the height of the object, r, from the center of the earth. It does not depend upon the mass of the falling object. Thus, acceleration due to gravity is same for all freely falling bodies irrespective of their masses. The value of G on the surface of the earth. Let us find the value of G on the surface of earth by substituting known values of G, M and R in the equation. G is equal to capital G capital M upon capital R square. We have G is equal to 6.67 into 10 raised to minus 11 Newton meter square upon kg square. Mass of the earth, m, is equal to 6 into 10 raised to 24 kg. radius of the earth r is equal to 6.4 into 10 raised to 6 meter. Substituting these values, we get G is equal to 6.67 into 10 raised to minus 11 into 6 into 10 raised to 24 upon 6.4 into 10 raised to 6 on the whole square. G is equal to 9.8 meter per second square. Hence, value of G on the surface of the earth is G is equal to 9.8 meter per second square. Why does an object thrown upward fall on the earth? The acceleration due to gravity is always directed vertically downwards. If an object is thrown vertically upwards, it moves in the direction opposite to that force of gravity, and hence the acceleration is in the opposite direction. Therefore, its velocity goes on decreasing and finally becomes zero at some height. From this height, the object begins to fall vertically downwards under the effect of the force of the gravity, due to which its velocity goes on increasing as it falls on the earth. Variation in the value of G. The value of G is equal to 9.8 meter per second square, but its value varies with the altitude, depth, and also due to the shape of the earth. A. With altitude, the value of G is given by G is equal to capital G capital M upon capital R square. Hence, R is the distance of the object from the center of the earth. Hence, value of G decreases with distance of the object from the center of the earth. In other words, the value of G decreases as one goes up above the surface of the earth or when the altitude increases. The value of G at different altitude is shown in the table. From the table, it is clear that when the altitude increases, the value of G decreases. B. With depth. When a body is taken inside the earth at a depth d, it experiences a force only due to the portion of the earth of radius r d. Thus, the value of G goes on decreasing as one goes deep inside the earth. The value of G becomes zero at the center of the earth. The value of G decreases when we go above or below the surface of the earth. Therefore, the value of G is maximum at the surface of the earth. C. Due to the shape of the earth. The shape of the earth is not perfectly spherical. It is flattened at the poles and bulges at the equator. Therefore, the radius of the earth at the poles is less than at the equator. The value of G is different at different places on the surface of the earth, ranging from a maximum value of 9.83 meter per second square at the poles to a minimum value of 9.78 meters per second square at the equator. For the practical purposes, the average value of G at on near Earth's surface is assumed to be 9.8 meters per second square. Motion of objects under the influence of gravitational force of the Earth. Let us do some activities. Activity 1. Take two balls of different masses and drop them from a top of a building. Which ball reaches the ground first? You'll find that both of them reach the ground at the same time. Activity 2. Take two similar pages from the notebook. Crumple one paper. Allow both the papers to fall on the ground simultaneously. What do you observe? The crumpled paper reaches the ground earlier than the other paper. Why? Air resists any object moving through it. Air offers more resistance to the flat paper because of its more area than the crumpled paper. So the crumpled paper reaches the ground earlier. Activity 3. Take a feather and a paper. Allow them to fall to the ground simultaneously. Which one falls first? The paper falls earlier than the feather. Now let us try the same activity in a glass tube from which air has been sucked out. Now which one will fall first? The feather and the paper fall at the same time. What can we understand from the above activities? All objects, hollow or solid, big or small, fall at the same rate if it falls freely.
Equations of motion for freely falling objects. The three equations of motion for objects that travel with uniform acceleration are given as v is equal to u plus a into t, s is equal to u into t plus half a into t square, v square is equal to u square plus 2 into a into s, where u and v are the initial and final velocities and s is the distance covered in time t with acceleration a. Since the freely falling objects fall with uniformly accelerated motion, these three equations of motion can be applied to freely falling objects. We can replace the acceleration a of the equations by the acceleration due to gravity g, which is constant near the earth. Also, since the vertical distance of the freely falling body is its height s, in the equations can be replaced by height h. On replacing, we get the modified equations of motion for freely falling objects as v is equal to u plus g into t, h is equal to u into t plus half g into t square, v square is equal to u square plus 2 into g into h. Note that the acceleration due to gravity is positive for a body falling vertically downwards. That is, g is equal to plus 9.8 meter per second square, whereas the acceleration due to gravity is negative for a body thrown vertically upwards. That is, g is equal to minus 9.8 meter per second square. Also, when an object is dropped freely from some height, its initial velocity u becomes 0, whereas if an object is thrown vertically upwards, its final velocity v becomes 0.
Now, let us solve one example by applying equation of motion. A boy drops a coin from the top of a building which is 49 meter high. Find the velocity with which the coin strikes to the ground. Solution. First, let us write the given data. Given u is equal to 0, g is equal to 9.8 meter per second square, s is equal to 49 meter. Substituting the values in the equation, v square minus u square is equal to 2gs. Since the coin travels in the direction of the gravitational force, v square minus 0 is equal to 2 into 9.8 into 49. V square is equal to 961. V is equal to the root of 961 is equal to plus or minus 31 meter per second. As the coin is traveling in downward direction, the negative sign is used. Hence, the velocity with which the coin strikes the ground is v is equal to minus 31 meter per second.
Mass and weight.
Let us do an activity. Find the weight of your book at a grocery shop using a pan balance. Find the weight of the same book at your laboratory using a spring balance. Are they same? Yes, they are same. As gravitational force acting on a body is same at places close enough, therefore the weight measured at these places will be the same. If the book is taken to a far away place, say at poles, its weight will be different, but the mass of the book at both places is the same. Now, let us define what is mass and weight. Mass of an object is the quantity of matter contained in it. Mass is a scalar quantity. Mass does not change from place to place. Mass can never be zero. If the mass becomes zero, the object will disappear. The SI unit of mass is kilogram, kg. Mass is the measure of the inertia of the object. The greater the mass, more the inertia. Weight. The weight of the body is the force with which the earth attracts it towards the center. By Newton's law of gravitation, the force of attraction is given as F is equal to G into capital M, small m, upon R square is equal to mg. Hence, G is equal to Gm upon R square. Since the weight of the body is the force of attraction, we can write the weight of the body, W, whose mass is m, as W is equal to mg. Therefore, the weight of the body changes from place to place as the value of G changes from place to place. Since the value of G is maximum at poles and minimum at the equator, The weight of the body is also maximum at poles and minimum at equator. The weight of the body decreases at higher altitudes such as mountains. The weight of the body is zero at the center of the earth and it is maximum on the surface of the earth. SI unit of weight is Newton, N. Let us solve an example to understand the weight of a body changes from place to place. Solved example. There is one body in space which has mass twice that of the earth and a radius thrice that of the earth. If the weight of a book on earth is 90 Newton, what will be its weight on that body? Solution. Let the radius of the body in space be Rs and that of the earth be Re. Let the mass of the body in space be Ms and that of the earth be Me. Let the weight of the book in the space be Ws and that on the earth be We. Given Rs is equal to 3 Re, Ms is equal to 2 Me, We is equal to 90 Newton. Weight of the book on earth, We is equal to Fe is equal to G into Me into M upon Re square. 1. Weight of the book on the body in space, Ws is equal to Fs is equal to G into Ms into M upon Rs square. 2. Dividing equation 1 by equation 2, we get We upon Ws is equal to Me upon Ms into Rs on the whole square upon Re on the whole square. Substituting the values, 90 upon Ws is equal to 1 upon 2 into 3 on the whole square. 90 upon Ws is equal to 9 upon 2. Simplifying, we get Ws is equal to 20 Newton. The weight of the book on the body in space is 20 Newton. The weight of the body on a planet. The weight of a body of mass m on a planet Wp is equal to mgp, where gp is the acceleration due to gravity of the planet, but gp is equal to g into mp upon rp on the whole square, where mp and rp are the mass and the radius of the planet respectively. Since mp and rp are different for different planets, the weight of the body will be different on different planets, even though its mass remains constant. Let us solve example to find values of G on the surfaces of the Moon and Mars. Solved examples. 1. Let us calculate the acceleration due to gravity Gm on the surface of the moon. We know mm is equal to mass of moon is equal to 7.4 into 10 raised to 22 kilograms. Rm is equal to radius of moon is equal to 1740 kilometer is equal to 17,40,000 meters is equal to 1.74 into 10 raised to 6 meter. G is equal to 6.67 into 10 raised to minus 11 Newton meter square per kg square. The acceleration due to gravity of the moon is given by the equation Gm is equal to G into mm upon Rm square. Substituting the values, Gm is equal to 6.67 into 10 raised to minus 11 into 7.4 into 10 raised to 22 upon 1.74 into 10 raised to 6 the whole square. Simplifying, we get Gm is equal to 1.63 meter per second square. The acceleration due to gravity on the surface of the moon is 1.63 meter per second square. Now, let us compare the acceleration due to gravity on the surface of the moon with that on the surface of the earth. The value of Gm, that is acceleration due to gravity on the moon, is equal to 1.63 meter per second square. The value of Ge, that is acceleration due to gravity on earth, is equal to 9.8 meter per second square. Therefore, Gm upon Ge is equal to 1.63 upon 9.8 is equal to 1 upon 6. Thus, the value of the acceleration due to gravity on the moon is only 1/6 of the value of the acceleration due to gravity on earth. 2. Let us now find the acceleration due to gravity on the surface of Mars. We know diameter of the Mars is 6,760 kilometers. Mass of the Mars is equal to 1/10 that of the Earth. The diameter of the Earth is 12,742 kilometers and acceleration due to gravity on Earth is 9.8 meter per second square. dm is equal to diameter of Mars is equal to 6,760 kilometers. Therefore, Rm is equal to 6,760 upon 2, which is equal to 3,380 kilometers. Me is equal to mass of Earth. Mm is equal to mass of Mars is equal to 1 upon 10 mass of Earth. De is equal to diameter of Earth is equal to 12,742 kilometers. Therefore, Re is equal to 12,742 upon 2 is equal to 6,371 kilometer. G is equal to acceleration due to gravity is equal to 9.8 meter per second square. G is equal to capital G into capital M upon R square. Therefore, Gm upon Ge is equal to mm upon me into Re upon Rm on the whole square. Substituting the values, Gm upon 9.8 is equal to 1 upon 10 into 6371 upon 3380 on the whole square. Therefore, Gm is equal to 1 upon 10 into 0.28146 into 9.8. Gm is equal to 3.48 meter per second square. Acceleration due to gravity on mass is equal to 3.48 meter per second square.
Thrust and pressure.
Let us do some activities. Activity 1. Take a piece of paper and press on it with your thumb. There is no effect on the paper. Now take a pin and press the pointed end of the pin against the same piece of paper. Can you see an impression of the pin on the paper? Do you notice any difference? The forces applied by the thumb and the pin on the paper are the same, but the effects produced are different. Activity 2. Take a brick, keep it vertically on a sand bed. An impression of the brick will be seen on the sand bed. Now keep the same brick in horizontal position on the sand bed. You can see the impression in this case also. What difference do you notice? The brick goes deeper into the sand in vertical position than in horizontal position. In both the positions, force exerted on the sand is the weight of the brick, which is the same in both the cases. But effects produced are different. Why? In both of these cases, force is acting perpendicular to the surface of the paper or the sand. The force acting on an object perpendicular to the surface is called thrust. In these cases, we have seen that the thrust applied to the paper and to the sand surface are the same, but it produces different effects. This is because the effect of the thrust depends on the area on which it acts. This quantity is defined as pressure, which is the thrust acting on the unit area. Thus, the thrust on a unit surface area is called pressure. Pressure is equal to thrust divided by area. SI unit of pressure is Newton per meter square. It is also called Pascal, PA, in honor of the scientist Blaise Pascal.
Let us solve our problems to understand the effects of thrust acting on different areas.
1. Calculate the pressure exerted in following position of wooden block. The dimensions of the block are shown in the figure. From figure, length of the wooden block is 80 centimeters, breadth is 50 centimeters, and the thickness is 20 centimeters. The weight of the block is 500 Newton. Let it be kept in vertical position. When the block was kept in a vertical position, the weight W of the block is distributed over the surface of contact, which is equal to the product 50 centimeters into 20 centimeters, that is 1000 square centimeter, which is equal to 0.1 meter square. Hence, the pressure on the surface in the first case is given by P is equal to W divided by A, which is equal to 500 divided by 0.1, which is equal to 5000 Newton per meter square. Now let us calculate pressure when the wooden block is kept in horizontal position with its surface 80 centimeters into 50 centimeters touching the floor. In the second case, the brick is kept horizontally such that the area in contact with the sand is 80 by 50, which is equal to 4000 square centimeter, which is equal to 0.4 meter square. Now the pressure acting on the sand surface in this case is P, which is equal to W divided by A, is equal to 500 divided by 0.4, which is equal to 1250 Newton per meter square, which is 1/4 of the pressure in the first case. Hence, large pressure is exerted on smaller area while less pressure is exerted on larger area by the same object.
Just look into your surroundings and locate examples where concept of pressure is put to use. We may start by using a knife to chop or cut vegetables. Knives, blades and other devices like scissors and needles have sharp edges or pointed tips. This makes chopping, cutting and stitching easy as the area of contact is less, resulting in greater pressure produced and making our work easier. Have you ever thought why ski boards that are used to glide over ice long and broad? The ski boards are made long and broad so that area of contact is increased. We know that greater the surface area, less is the pressure produced. This makes it easier to slide over ice. It is for the same reason that school bags have broad shoulder straps. The broad straps distribute the heavy weight of the bag over a larger surface area on the shoulders, thus reducing the pressure on the shoulders of the students considerably and making it easier for them to carry such heavy bags.
Now, let us solve some problems based on pressure.
Solved examples. 1. Calculate pressure exerted by a screw on the wooden plank if the area of contact of the screw is 0.5 millimeter square and its weight is 1 Newton. Solution. Let us write the given quantities in proper units, that is SI units. Given area, which is equal to 0.5 millimeter square, which is equal to 0.5 multiplied by 10 raised to minus 6 meter square. Weight of the screw is equal to thrust, which is equal to 1 Newton. The pressure exerted by the screw is given by pressure is equal to thrust divided by area, equal to 1 divided by 0.5 multiplied by 10 raised to minus 6 is equal to 2 multiplied by 10 raised to 6 Newton per meter square. Hence, the pressure exerted by the screw on the wooden plank is 2 multiplied by 10 raised to 6 Newton per meter square. 2. Calculate pressure exerted by the metal block when it is made to lie on the tabletop with the surface A. ABCD, B. DCFE, C. BCFG. State in which position is the pressure maximum. Solution. The thrust on the table by the block is the weight of the metal block. Thrust is equal to weight of the metal block is equal to mg, which is equal to 10 into 9.8, which is equal to 98 Newton. A. Let the block be placed on the table with the surface ABCD touching the table. For the surface ABCD, length is equal to 50 centimeters and breadth is equal to 20 centimeter. Area is equal to length multiplied by breadth is equal to 50 centimeter into 20 centimeter, which is equal to 1000 centimeter square. Area is equal to 0.1 meter square. Hence, the pressure exerted on the table by the block is given by pressure is equal to thrust divided by area, which is equal to 98 divided by 0.1. Pressure is equal to 980 Newton per meter square. B. Let the block be placed on the table with the surface DCFE touching the table. For surface DCFE, length is equal to 50 centimeter, breadth is equal to 10 centimeter. Area is equal to length multiplied by breadth. Area is equal to 50 centimeter multiplied by 10 centimeter, which is equal to 500 centimeter square, which is equal to 500 into 10 raised to minus 4 meter square. Area is equal to 0.05 meter square. Hence, the pressure exerted by the block on the table given by pressure is equal to thrust divided by area. Pressure is equal to 98 divided by 0.05, which is equal to 1960 Newton per meter square. C. Now let the block be placed on the table with the surface BCFG touching the table. For surface BCFG, length is equal to 20 centimeter, breadth is equal to 10 centimeter. Area is equal to length multiplied by breadth equal to 20 centimeter multiplied by 10 centimeter, which is equal to 200 centimeter square, which is equal to 0.02 meter square. Pressure is equal to thrust divided by area. Pressure is equal to 98 divided by 0.02, which is equal to 4900 Newton per meter square. The pressure will be maximum when surface BCFG lie on the table. That is, pressure will be maximum when the area is minimum. Pressure in fluids. Let us do an activity. Let us take 2 rubber balloons. Let us fill one with water and blow air into the other. Let us prick both the balloons with the pin. What do you observe? You observed air and water rushing out of the balloon with speed. The pressure inside them makes this possible. Liquids and gases exhibit the property of flowing and hence they are called fluids. Fluids exert pressure on all sides of the container that holds them. Pressure inside a fluid is due to its weight. Fluid also exerts pressure on all bodies immersed in them. Pressure inside a fluid is same everywhere. If we exert pressure in any part of the fluid, it is transmitted undiminished in all directions. You must have observed that gases take shape of the container and they don't have any specific volume. Gases occupy all the space available to them with uniform pressure. Gases don't have any free surface. Liquids are differentiated from gases by their properties of possessing a definite volume at definite temperature. Like gases, they do take shape of the container, but they can have free horizontal surface if not completely confined. Like gases, liquids also exert pressure. Liquids exert pressure on bodies immersed in it. At a point in the liquid, the pressure is the same in all directions. The pressure at any point under the liquid is due to weight of liquid column above that point. A swimmer can experience the change in pressure as he dives deeper in the water. During swimming, weight of the body is supported by water because of the high liquid pressure on the lower surface of the body compared to the pressure at the upper surface. If this difference in pressure is more than the weight of the body floats, else the body sinks in the liquid. From this activity, it is clear that at a given depth, pressure remains the same in all directions. Pressure is independent of size and shape of the container, but it depends on the height or the depth of the liquid. Pressure increases with depth. It also depends upon density of liquid. Buoyant force. Let us do some activities before we discover what is a buoyant force. Activity 1. Take a bucket full of water. Take a glass bottle. Try to push the bottle in inverted position into the bucket. What do you experience? It is difficult to push the bottle inside the water. Activity 2. Take an empty plastic bottle, closed with an airtight stopper. Put it in the bucket full of water. What do you observe? You will observe that it floats on the water. Now try to push the bottle into the water. Is it possible to push it easily to the bottom of the bucket? No. It takes a lot of effort to hold the bottle at the bottom. Now release the bottle. What happens to it? The bottle quickly rises up and floats on the surface. The force acting on the bottle in the upward direction is called as upthrust or buoyant force. When a body is partially or fully dipped into a liquid, the liquid exerts forces on the body. The force exerted by the liquid is perpendicular to the surface of the body and is equal to the product of pressure and the area at that point. The resultant of these contact forces is called a buoyant force. When an object is immersed in water, this buoyant force acts on it, causing apparent losses of weight. Have you ever drawn water from a well? You would have noticed that the bucket of water appears lighter underwater but heavier as it comes out of water. Thus, a submerged object appears to lose weight in the liquid due to upthrust or buoyant force. The property of liquid to exert an upward force on an object immersed in it is called buoyancy. The buoyant force acting on an object depends on 1. Volume of the object. The buoyant force is greater if the volume of the object submerged in the liquid is larger. 2. Density of the liquid. The buoyant force is greater if the density of the liquid is greater.
Have you ever wondered why do objects sink or float when placed on the surface of water? Let us understand this by performing an activity.
Let us do an activity. Take an iron nail and a plastic cap of a bottle having nearly equal masses. Put them in water. What do you observe? You will observe that the plastic cap floats while the iron nail sinks to the bottom. What makes one of the objects to sink in a liquid and the other object to float in the same liquid? Let us find an explanation for this. The weight of the object always acts in the downward direction while the buoyant force acts in the upward direction. The buoyant force determines whether an object will float or sink in a liquid. A. If buoyant force exceeds the weight of the object floats. If the weight of object exceeds the buoyant force, the object sinks. C. If the buoyant force is equal to the weight of the object, then the object floats inside the liquid. Archimedes' principle. Let us do this activity. Take a piece of stone and tie it to one end of a rubber string. Measure the length of a rubber string before suspending. Note that it is equal to 50 centimeters. Now suspend the stone by holding the string as shown. The string gets elongated. Measure its length in this state. It is 55 centimeters. Now slowly dip the stone in the water in a container as shown in the second case. Observe what happens to elongation of the string. Measure the length of the string in this state too. You will find that the elongation of the string decreases as the stone is gradually dipped in the water. Now measure the length of the string. It is 53 centimeters. But there is no further change once the stone gets fully immersed in the water. The explanation of this is given by the Archimedes principle. the elongation is produced in the string due to weight of the stone. The extension decreases when the stone is lowered in water. It means that some force acts on the stone in an upward direction. This is the buoyant force acting on the body. The magnitude of this buoyant force can be determined by Archimedes' principle. Archimedes' principle. Statement: when a body is immersed completely or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. About Archimedes. Archimedes was a great Greek scientist. He was assigned a job by the king to verify the purity of the gold used in the crown. He discovered the Archimedes principle after noticing that the water in a bathtub overflowed when he stepped into it. He ran through the streets shouting, "Eureka!" means "I have got it." Using this principle, he determined the purity of the gold in the crown. His work in the field of geometry and mechanics made him famous. His understanding of levers, pulleys, wheels and axle helped the Greek army in the war with the Roman army. Application of Archimedes' principle. 1. It is very useful in designing ships and submarines. Submarine is a ship which can float on the surface of the sea or can sink when necessary and reappear again on the surface. It is provided with large tanks both at the front and at the back. These tanks can be filled with seawater or air from compressed air reservoirs. If the tanks are filled with water, the weight of the ship increases and hence it sinks according to the requirement. Hence, the buoyancy force exerted on the submarine is less than the weight of the submarine. If water from tank is pumped out by forcing compressed air in them, now the ship becomes lighter and rises to the surface because the buoyant force in this case is more than the weight of the submarine. The submarine is such designed that the weight of the water is displaced by the submarine when filled with air is more than the weight of the submarine. 2. Various instruments like lactometer, hydrometer are based on this principle. Lactometer is a device used to determine the purity of sample of milk, while hydrometer is used to determine density of the liquid. The depth to which these instruments dip in the fluid depends on the density of the fluid.
Let us do a quick check. relative density. An object floats or sinks in a liquid depends whether its density is less or more than the density of that liquid. Let us understand this by performing an activity.
Activity. Take a piece of aluminium foil and put it in the bucket full of water. What do you observe? It floats on the water. Now crush the foil into a ball and put it in the same bucket. Now what is your observation? Now the ball of crushed foil sinks to the bottom. Now put the ball of crushed foil into a bowl of mercury. What happens? It floats in mercury. This is due to change in the density. Aluminium foil has a large surface area. Its density is low. When it is put gently in the water, it floats over it because its weight is less than the buoyant force. When the aluminium foil is crushed to form a ball, the volume of the ball is small and hence has more density. The buoyant force is less than the weight of the ball. Hence, it sinks in water. When it is put into a bowl of mercury, it floats. As the density of mercury is much greater than water, upthrust is also greater and the ball floats. Density of a substance is the ratio of its mass to its volume. Its SI unit is kilogram per meter cube. Density is equal to mass divided by volume. The density of a substance is one of its characteristic property. For specified conditions, density of a substance remains the same. It is different for different substances. The density of a substance is useful to determine its purity. An object sinks in a liquid if its density is more than the liquid, while if density of an object is less than density of the liquid, it floats. Density of a substance is compared with that of water and expressed as relative density. The relative density of a substance is the ratio of its density to that of water. Relative density is equal to density of substance divided by density of water. It is also called as specific gravity of a substance, as it is the ratio of the two similar quantities. It has no unit.
Let us solve an example based on relative density. Let us do a quick check.
If the density of water is 10 raised to 3 kilogram per meter cube and density of copper is 8.9 multiplied by 10 raised to 3 kilogram per meter cube, calculate relative density of copper. Solution. Given density of water is equal to 10 raised to 3 kilogram per meter cube. density of copper is equal to 8.9 multiplied by 10 raised to 3 kilogram per meter cube. We want to find the relative density of copper. It is given by relative density is equal to density of copper divided by density of water, which is equal to 8.9 multiplied by 10 cube divided by 10 cube, which is equal to 8.9. Therefore, relative density of copper is 8.9.